Welcome to this video on the architecture of chance. We begin by defining the sample space, which is the universal set of all possible outcomes for an experiment. An event is simply a subset of that space. Events have a taxonomy. We can have an impossible event with no outcomes, a simple event with one point, a compound event with multiple points, or a sure event containing all outcomes. To see this in practice, consider rolling a standard die. An impossible event would be rolling a multiple of 7, while a sure event is rolling any number that is odd or even. When tossing 2 coins, a simple event is getting 2 heads, whereas a compound event is getting at least 1 head. The algebra of events allows us to manipulate these sets using operations like not A or B, A and B, and A but not B. Applying these operations to rolling a die, where A is a prime number and B is an odd number, shows us how these different set combinations result in distinct subsets. Events are mutually exclusive if they cannot occur simultaneously, meaning their intersection is empty. Conversely, events are exhaustive if their union covers the entire sample space, ensuring at least one of them must occur. This matrix helps us compare these concepts, highlighting how events can be mutually exclusive, exhaustive, or both, which creates a perfect partition. The axiomatic approach to probability relies on 3 foundations: non-negativity, the certainty of the total sample space, and additivity for mutually exclusive events. These axioms anchor probability between 0 and 1, establishing that the sum of all elementary probabilities in a sample space must equal 1. For equally likely outcomes, we use this master formula. The probability is the number of favorable outcomes divided by the total number of outcomes. Because an event and its complement are mutually exclusive and exhaustive, the probability of not A is simply 1 minus the probability of A. Finally, the addition theorem reminds us that when finding the probability of a union, we must subtract the intersection to avoid counting those outcomes twice. When we calculate the union of 2 events, we must account for their overlap. By subtracting the probability of the intersection once, we resolve double counting and ensure each sample point is counted exactly once. In the special case where events A and B are disjoint, they cannot occur simultaneously. Their intersection is an empty set, simplifying our formula to just the sum of the individual probabilities. This final synthesis connects set algebra with the rules of probability, demonstrating how logic provides the foundation for measuring chance.